All of you know that gold, copper, and iron are metals. What about mercury and silicon? Are they metals or non-metals? Can you tell by just looking at them? Which element is more reactive, iron or copper? And if you are asked which atom is the biggest, aluminium, iron or copper, can you answer without referring to the values of their atomic sizes? Building up the periodic table has been a major scientific achievement. The broadest distinction in the table is between the metals that lie on the left-hand side and the non-metals placed in the top right region. The zigzag line separates the metals on the left from the non-metals on the right. These elements are called metalloids or semi-metals and show some properties of the metals and some that are more characteristic of the non-metals. Out of 94 naturally occurring elements, 70 can be classified as metals. Metals have 1, 2, or 3 valence electrons. Metals are electropositive in their nature. To achieve the nearest noble gas configuration, metals lose 1, 2, or 3 valence electrons while forming bonds. Hence, the valency or combining capacity increases as we move from left to right across a period within the metals. Non-metals are electronegative. The number of valence electrons in non-metals varies from 4 to 7. An atom of carbon has 4 valence electrons. Nitrogen has 5. There are 6 valence electrons in an atom of oxygen, and 7 valence electrons are present in an atom of fluorine. To achieve an octet, nonmetals need to share electrons or gain electrons. Nitrogen gains 3 electrons to attain an octet. The valency of nitrogen is -3. Oxygen needs only 2 more electrons to achieve an octet. The valency of oxygen is -2. And fluorine needs 1 electron to achieve stability. Hence, the valency of fluorine is -1. As we move across a period, the valency of nonmetals decreases from 4 to 1. How does the valency of elements vary in a group? Lithium, sodium, and potassium each have only 1 valence electron. To achieve an octet, atoms prefer to lose this single electron. Hence, the valency of elements in a group is constant. Is this trend seen in group 2 as well? Yes. All elements in group 2 prefer to lose the 2 valence shell electrons and form dipositive ions. As we go down a group, the valency of elements remains the same. The term atomic size refers to the radius of an atom. Let's take a look at the variations of atomic size. How does atomic size vary in a group? The atomic radius increases in spite of the increasing nuclear charge. Why? This is because the number of electron shells is also increasing. Let us compare the atomic radii of elements of group 1. Hydrogen has one shell occupied by a single electron. Its atomic radius is 37 picometers. Lithium belongs to the second period and has 2 electron shells. As a result, it has a greater atomic radius than hydrogen. The atoms of group 1 increase in size as successive electron shells are added. This trend is seen in all groups of the periodic table. As we go down the group, the number of electron shells gradually increases. The shells envelop one another like the layers in an onion. As a result, the atomic radius increases despite increasing nuclear charge. How does the atomic radius change from left to right in a period? Consider elements of period 2. The atomic size decreases as we move from left to right across a period. Is this trend seen in period 3 too? Yes. As we move across a period, there is an increase in the nuclear charge. This pulls the electrons closer to the nucleus. Therefore, the sodium atom's radius is larger than the magnesium atom's. In period 4, a potassium atom has a radius larger than a calcium atom's. In a similar fashion, the alkaline earth metals in group 2 are smaller than their respective neighbors, the alkali metals in group 1. Sodium, with atomic number 11, has a single valence electron in the third shell. The atomic number of magnesium is 12. The nuclear charge also increases by 1. This causes the attractive forces between the nucleus and the electrons to strengthen. This effect is counteracted by the increasing number of electrons, but the increased nuclear charge is the stronger factor. Thus, the atomic radius is reduced. To sum up, in the period table, the atomic radius decreases from left to right along a period. Metallic character is the tendency to lose electrons, and the non-metallic character is the tendency to gain electrons during bonding. Metals tend to lose electrons when forming bonds. That is, they are electropositive in nature. Down the group, the effective nuclear charge experienced by valence electrons decreases because the outermost electrons are further away from the nucleus. Therefore, metallic character increases down a group. Across a period, as the effective nuclear charge acting on the valence shell electrons increases, the tendency to lose electrons decreases. Hence, metallic character decreases across a period. Unlike metals, which are electropositive, the nonmetals are electronegative. Electronegativity is the tendency of an atom in a molecule to attract the electrons of a bonding pair toward itself. This quality depends upon the size of the atom, the number of valence electrons, and the effective nuclear charge. Moving across a period, the atomic radii of the elements decrease, but their electronegativity increases. The number of valence electrons increases from 1 in sodium to 2 in magnesium, 3 in aluminium, 4 in silicon, 5 in phosphorus, 6 in sulfur, and 7 in chlorine. Electronegativity increases with an increase in the number of valence electrons. Electronegativity also increases with the increase in effective nuclear charge. Does the electronegativity increase as we move across a period? This graph reflects the trend in electronegativity across period 3.